Hi, everybody, and welcome to Echo Live. My name is Anna, and you might notice that I am sitting somewhere kind of different today, maybe a little bit of a strange place, not the place we're used to seeing behind me for virtual programs, but I am actually back at the Michigan Science Center today. I'm so excited to be back in the building, doing a little bit of work to get us prepared to reopen to the public very soon. So hopefully some of you who have been tuning in to Echo Live, oh, my thing is echoing back at me. Let me set that up. But we are so excited to be welcoming everyone to the building very, very soon. So some of us are here in the building just getting everything cleaned and organized and ready. And so we're so excited that some of you who've been tuning in online might get to visit us here in person very, very soon. But don't worry, Echo Live is not over just yet. And today we have another very exciting program planned with our staff astronomer and solar system ambassador, Paulette. So Paulette is here to talk to us about some space content. As always, go ahead and use the chat feature to introduce yourself. Let us know that you're here and watching, but also let us know if you have any questions about space, about stars, or about physics, about anything that Paulette is here to talk to us about today. I see some people chiming in the comments already, especially congratulations to Leanne. I can see that today is Leanne's last day of 4th grade, and she is going to be officially a 5th grader. That's so cool. Congratulations. Congratulations to all of you who might be graduating 1 grade and moving on to the next. We hope, of course, that you'll still continue to tune into Echo Live. And with that, I'm going to let Paulette take it away for another really exciting virtual planetarium show for us today.
All right. Hi, everyone. So Anna is in the building. I am also at the Michigan Science Center prepping everything so that we're ready to go. Sometime in July, we hope to be opening up for you guys, and we'd love to see you come in once we do that. But we still don't have a date quite yet. We're working on it, but sometime in July, hopefully we'll have the Michigan Science Center open back up again. So today we are going to be talking a little bit about stars. So we've seen some of the stars up in the nighttime sky, and we've also been able to visit all of our planets, but we're going to really focus today about what those stars are like, why those stars do something, why they burn, how they burn, and how they live and die. So we're going to talk a little bit about that today. And first, we want to talk a little bit about how stars are able to live. So essentially what happens is inside of stars, hydrogen smashes into other hydrogen and it becomes helium, something that we call thermonuclear fusion. And because of that thermonuclear fusion, energy is produced. So if we have a star like my handy dandy red balloon right here, it goes through something that we call hydrostatic equilibrium. And I know that's a really big word, but hydrostatic equilibrium just means that the pressure or the energy from the inside equals the pressure or the energy from the outside. Now, we'll talk about that more in a little bit when we start talking about the lifetimes of those stars. But let's go ahead and jump into our virtual planetarium so that we can see some of the stars that we might have up in our nighttime sky. So we're using a program that we have used before. Again, this is a free program called Worldwide Telescope. Worldwide Telescope allows us to be able to see not just what's up in the nighttime sky, but it also allows us to zoom in on some of the amazing images that some of our telescopes have looked at. So if you joined us on the Hubble Space Telescope program, you might have seen us use Worldwide Telescope in the past. Now, when we look at these stars, do all stars look the same? That's my question for you today. Do all stars look the same?
Paulette, we've had some requests that maybe you adjust your microphone just a little bit. Apologies, everyone. We can tell it's just a little bit quiet. We are working with a whole new setup here today, so just bear with us.
All right, so again, do all stars look the same? Is that a little bit better, Anna?
I think it's a little bit better, but let us know in the chat, you guys. If you still can't hear, we'll just have Paulette maybe project a little bit.
Yeah. Oh, here we go. Is that better?
A little echoey, but definitely louder. So I would say go with that.
All right, so we're gonna move the microphone back over here. We're gonna have, there we go. Okay, so are we doing a little bit better? Some stars look the same. All right, so we've got some folks telling us we do look better. So do all stars look the same? Some stars look the same, but not all of them. And some stars all look a little bit different. So as we're looking at sort of our virtual planetarium here, does this star look the same as this one right here? And if the answer is no, what looks different about those two stars? This star right here and this one right here, do they look the same? And if the answer is no, what's the difference between the two of them? This star and this one. Someone just told me in the chat that the colors are a little bit different. And that's right. We have our nice bright red star right up over here called Betelgeuse. And right down over here, we have a nice bright blue star named Rigel. Stars come in different colors. Those different colors mean that the stars are different temperatures. So the red stars are the cooler ones. The blue stars are the hotter ones. And I know that seems a little bit opposite than what you might think, because when you wash your hands, red is hot and blue is cold. Now, the stars that we have up in the sky are not necessarily cold. They just get a little bit cooler. There's still a couple of thousands of degrees, but the blue stars are a couple of tens of thousands of degrees. So these two stars are different colors. What else might we notice about some of the stars up in the sky? Say if we compare this blue star to this blue star right here. What might be the difference between those two stars that we see up in the sky? We have some folks chiming in already. We had the color difference here, but we have a blue star here and a blue star here. What's the difference between those two stars? We have some folks telling us the size is different, and that's right. The brightness is also different. So Sirius is actually the brightest star up in the nighttime sky, and I call it a seriously bright star. I apologize for those of you that have been watching our program. You get to hear the same jokes from me all the time. So here we have a much brighter star than Rigel over here, but it turns out that those stars are also different sizes. So if we take a look at something that we call the Hertzsprung-Russell Diagram, you don't have to remember the name of that, I promise. You'll actually be able to see how stars sort of are classified. We have our red stars. So here we've got temperature. See, blue is the really, really hot. And it goes all the way down to red. So here we have the blue and red. And then we have the brightness of the stars going up this direction. So the stars that we have up in our sky that are very, very bright are some of our larger stars. So for example, we were able to see Betelgeuse, which is a supergiant star, right up over here. Then we also have a few giant stars, and we also might be able to see some teeny tiny little white dwarfs as well. So we call this right here the main sequence because most stars are within this area right here.
But sometimes the stars will leave the main sequence to go up to giants or supergiants and back down to our little white dwarfs. Now, where is the sun in our diagram here? Is it a giant, a supergiant, a main sequence star, or a white dwarf? Where is our sun? Is it a supergiant, a giant, a white dwarf, or a main sequence star? It turns out that the sun is right here in our main sequence. Our sun is a yellow star, or at least it falls within the yellow part of the spectrum, right around 6,000 degrees. So here we have our sun. So this is sort of how we classify some of the stars that we see up in the sky. But not all of these stars are within the same part of their lifetimes. Stars start in a giant cloud of hydrogen gas. So let's go ahead and switch back over to our virtual planetarium. And let's take a look at one of those star-forming regions. Right here, we have a star-forming region called the Great Orion Nebula. The Great Orion Nebula. And let's zoom in on that a little further and use an image from the Hubble Space Telescope. Michelle said that our sun is just a regular old star, and that's true. It's pretty average. But because it's average, that's why we're able to have life on the Earth. So here we have one of those star-forming regions that's made mostly out of hydrogen gas. And that hydrogen gas will then start to clump together. So we can think about maybe sort of starting to make a snowball. If you make a snowball, you take a little bit of snow, and then you pack more and more and more and more snow on top of it. Well, that's kind of what's happening in these star-forming regions. We have these brand new baby stars that are just being formed and that are pulling that hydrogen gas into them. So the hydrogen gas is creating these stars that we see, these protostars that we see in these star-forming regions, made again mostly out of hydrogen gas. That hydrogen then turns into helium because of collisions that are happening. So these hydrogen atoms are banging into each other and forming helium gas and also forming energy. That energy is what keeps the balloon inflated. That's what keeps the stars from collapsing down. Because what do we have on the outside of the balloon? Inside our stars, we have the energy that's produced from that thermonuclear fusion. But what do we have on the outside of the stars and on the outside of our balloon here, pushing on the surface? Let me stop the share. All right, so we have our balloon. What do we have pushing on our balloon, which also is something that might be a force pushing on our stars? We've talked about it in our Echo Live program in the past. Someone has a really good guess in Zoom. You said air. Fantastic guess. It isn't actually, well, here on the Earth, yes, we have air. Air is pushing on our balloon, but there's something else that's pushing on our balloon. And remember, there's no air in space, but there is gravity. Helena, you have it right. Gravity is pushing on the balloon and pushing down on our stars, and the energy from the inside is pushing out the other way. So, like I said, we have a hydrostatic equilibrium because that balloon or that star maintains its same shape. Now, if we go through the whole stellar lifetime, we can take a look at what happens. So, I said that we start with our protostar. All stars start the same way. So all stars start as protostars in that stellar nursery, like one that we see in the Great Orion Nebula. Those protostars sometimes are really, really big and sometimes are not so big. So right down here, we have a very small protostar that turns into a type of star that we call a brown dwarf. That brown dwarf actually lives for a really long time. And that's because it's not using up a ton of its hydrogen, so it's able to burn the gas that's inside of it, or the plasma inside of it, for a really long time. As the stars get larger, we can see that they might not live quite as long. For example, this protostar right here turns into a blue supergiant and has a really, really short life before it collapses down into something we call a black hole. So the larger the star, the shorter the lifespan. Now, our sun is right here. We have sort of a medium-sized protostar that turned into a medium-sized star. And we do have a stellar lifetime. So it'll go through some different phases of its lifetime. We go from a solar type star to a red giant. So remember, on that main sequence, our sun is actually going to pop up to right here and be a red giant star in about 4 billion years or so. So don't worry, not going to happen within our lifetimes. When it becomes a red giant, it's going to expand and actually expand so far that it's going to eat the orbits of the Earth and maybe even the orbit of Mars. We're not quite sure. But again, that won't happen until about 4 billion years. And when it uses up all of its energy as a red giant, it just sort of slowly deflates back down into a white dwarf. So we'll have a lot of gas that gets that we can see right here in the planetary nebula. And that gas is sort of expelled out, but there is really no explosion when it comes to the sun. It just sort of slowly condenses back down into the white dwarf and leaves gas along the outside. Now, I can actually show you an example of a planetary nebula. If I move back over to our virtual planetarium, we're going to be able to see our sky right here. And let's go ahead and let's head to, here we go, something called the Helix Nebula. As we head to the Helix Nebula, we'll be able to see that planetary nebula. So you can actually see that all of the gas around the outside of the star has just sort of expanded out, and we have right here in the center a white dwarf. So this is how our sun is actually going to end its life, by just slowly deflating like our balloon might slowly deflate. Now, when we have a very massive star, then what happens when we have a very massive star and it has used up all of its fuel? What do you think would happen if I took all of the air pressure out from inside this balloon, or all of the energy out from inside of a star? What do you think would happen to it? What do we think is going to happen if I take all of the energy out of this balloon? It deflates. And if it has a ton of energy inside of it, it pops and it explodes. So somebody asked what a supernova is. That is what a supernova is. The energy inside of that balloon overcame the gravity pushing down on it, and we have our supernova, or our explosion. So if we go back over to our other screen here, we're able to see that we have some steps where a protostar can become a blue supergiant, which then turns into a red giant, and it kind of contracts a little bit, and all of a sudden it turns supernova. If it's not quite big enough, it might go supernova and form a neutron star, or if it's really, really, really big, it's going to go supernova and turn into a black hole. So there's two different, there's a couple of different ways that stars will end their lives. They'll either end their lives as a brown dwarf, a white dwarf, a neutron star, or a black hole. Now, black hole is someplace that is sort of infinitely dense. So it squishes everything down into a teeny tiny little area. And that teeny tiny little area doesn't let light escape. So that's something that we call a black hole. And that only happens when a really, 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 really big star collapses down into that tiny little space. But we've actually been able to see the evidence from something like supernova, and we've actually been able to see supernova happen within if people go outside, they can actually sometimes see supernova happen. Now, this hasn't happened with us in a really long time, but in 1054, there was a huge supernova explosion that was actually able to be seen from the nighttime sky. So if we look right here, this is the remnants of that supernova explosion. This is something that we call the Crab Nebula. So a very large star ended its life and collapsed down into what we see here. It collapsed down, and it collapsed down so fast that it exploded. So here we can see that explosion and the debris that comes from that. And right here, we can actually see, this one has a neutron star inside of it, but there are others that do have black holes. So this nebula that we see is the Crab Nebula, and was from an explosion that we could see in 1054. And we can see the remnant still there, which is pretty exciting, I think. So we have all of our stars that are up in the sky, but most of the stars that we see, especially these very, very bright stars that we see up in the sky, are very unique. They're very strange because stars tend not to be individual up in the sky. They tend to be within something that we call a cluster. So if we look right over here, you might see a cluster that we've talked about before on Echo Live. This is the Pleiades star cluster. So the Pleiades star cluster is a collection of stars that are orbiting around the same center of mass. So they're all orbiting sort of around each other and clustered together, not just their apparent position up in the sky, but actually creating a cluster of themselves. Now, the Pleiades star cluster is something that we call an open cluster. There are also other types of clusters called globular clusters. So let's see if I can find our globular cluster. Here we go. We have one right up over here. And you can see, well, this one's still kind of an open cluster, but when we have a globular cluster, they glob together really, really close, which is why we call it the globular cluster. Open clusters, the stars are fairly spread out. Globular clusters, those stars are globbed together, which is where it gets its name. Here, I think this is a good example of, there we go. We have a good example of a globular cluster right here. All of those stars orbiting around each other are sort of all globbed together. So we have stars that are, we've talked about today, this sort of the stellar lifetime. So remember, they start as a protostar, and then they move up depending on their size through sort of these ranks. But for the most part, stars spend most of their lives within the main sequence that we see right here. Most of the stars that we see spend most of their lifetime here in the main sequence. Now, somebody asked a really, really great question in Zoom. Can Jupiter become a star? And you know, the reason I think that's such a great question is because Jupiter, as we've talked about in Echo Live, is made mostly out of hydrogen gas. So there's a lot of hydrogen gas in the atmosphere of Jupiter. But Jupiter is not quite big enough to start that thermonuclear fusion that it would need to become a star. So unfortunately, Jupiter is never going to become a star because it's not quite big enough. It would have to be quite a bit bigger than what it is right now to be a brown dwarf. And then, of course, our sun is way, way, way bigger than Jupiter. And it's somewhere right here in the middle of that main sequence. So fantastic question. And unfortunately, it's not going to become a star. It's just going to be a planet for the rest of its days. All right, so we've talked about the main sequence, we've talked about where stars spend most of their lives, and we've also talked a little bit about how stars evolve over time and how stars are formed. So does anybody have any questions for me? Any questions today? While we're waiting for some of those questions, Anna?
As always, we'll take just a minute to thank the sponsors of the Michigan Science Center. We are so thankful that we've been able to provide so many of our Echo Live programs to you for free, thanks to donations from our sponsors like Denso and the Ford Motor Company Fund. Our sponsors allow us to continue bringing these programs to you every weekday through the rest of June. So we've got a lot of Echo Live still coming your way, even though we know it's summer vacation. We do hope that you guys will continue to tune in, ask great questions, enjoy the programs that both Paulette and I and Raul have been doing so far. But what's really exciting is once our building reopens, we will start having even more presenters able to bring programs, because we'll actually be able to set the studio back here at the Science Center, and you'll get to meet all sorts of new faces. It's going to be so fun and exciting, but don't worry, Paulette and I will still be here to bring you programs as well. Do you see any questions in the chat that you want to get to just now, Paulette?
I did. I saw the question from Steve. He said, what are you talking about? Jupiter is huge. And you're right. Jupiter is really, really big, but to become a star, it would have to be like 3 times bigger than it is right now. So even though Jupiter is really, really big, it's just not quite big enough to become a star. We also have another great question about how does a protostar form? And the protostars form by moving gas out in space. So basically, when a supernova happens, or a planetary nebula happens, or star formation happens, it'll push the gas towards the rest of it. So it'll start to sort of move around in space. And then those hydrogen atoms can get close enough together to collide and have that thermonuclear fusion that we talked about today. And I also see somebody, I think Leanne said it's her birthday. So happy birthday.
Leanne, it's such a big day for you. Last day of school, first day of summer. It's your birthday. Happy birthday from all of us here. We hope you'll come visit us very soon. I know you're just down the street over in Dearborn, but if you come to the Science Center, I promise Paulette will sing to you because she's an amazing singer. All right, if that is all the questions we have for now, of course, we hope we'll see you back here tomorrow for another episode of Echo Live. Raul is going to be here to teach you all some science life hacks. So some science tricks that are going to make your lives a little bit easier, maybe a little more eco-friendly even. So it's going to be a really exciting program. We hope we'll see all of you back here tomorrow for more Echo Live. With that, have a great rest of your day, and we'll see you back here next time. Bye, Paulette.
Bye.